is the fourth video in our series on ring theory. And today we're going to look a little bit more at factorization in rings in a general sense. So in the previous video, we looked at factorization in rings that are maybe slight generalization of the integers. And now we want to abstract that a little bit, although we will be looking at some examples. So throughout this video, we'll say that R is a commutative ring with 1 and D is an integral domain. Now let's look at some definitions to get off the ground. So for A, B, and R, we say that A divides B, and we write, well, I would read that just as A divides B, but we've got a vertical line between A and B. Okay, so we say A divides B if there exists a C in R with B is equal to A times C. Now observe that that means that B is a multiple of A. So saying that A divides B is equivalent to saying that B is a multiple of A. Now, furthermore, if C is a unit, recall that a unit is an invertible element, then we say that A and B are associates. So in terms of factorization, associates are essentially the same. Now, a non-zero non-unit P is called irreducible if whenever P is equal to A times B, either A or B is a unit. So you might remember from elementary school that a prime number is something that's only divisible by itself and 1. And this definition for an irreducible element looks very similar to that. And that's because this notion of an irreducible element is in fact a generalization of the notion of a prime element in the integers. But it's not exactly the same because the true notion of a prime element in a ring requires something a bit stronger. And as we'll see later, there are most definitely irreducible elements that are not prime. Okay, so let's look at the definition of a prime element. So a non-unit P, which is also non-zero, is called prime if whenever P is equal to A times B, or sorry, P divides A times B, we know that P divides A or P divides B. Okay, so I just said that not all irreducibles are prime, but in fact all primes are irreducibles. And this is really in any commutative ring, but we're going to stick here with an integral domain because we're mostly specializing to integral domains for a bit. Okay, so let's see how this proof goes. So let's suppose that we have a prime, so we'll say P in D is prime, and we know that P is equal to A times B. So observe that's the setup for our irreducible element. Now we want to show that A or B is a unit given that P is prime. This shouldn't be too hard. Let's observe this means that P divides A times B because P is equal to A times B. P divides itself for sure. But now observe that means that P divides A or P divides B by the definition of a prime element. Now, without loss of generality, let's just assume that the one divisible by P is A. We can just rename A and B so that this is the case if we're worried about that. So let's put that down. So without loss of generality, assume that P divides A. But what does that mean? So that means that A is equal to M times P for some M within the ring. Notice here we're using the definition of divisibility over here. And see what I did there? I've got M times P. Oh, and I guess we're working within this integral domain. So let's change that to D. But now what we can do is put this equation right here for A back into this equation up here for P. So what does that give us? So we're going to have P is equal to M times P times B. Okay, so I think that's pretty clear. But now we can use the fact that we have cancellation within an integral domain. Now we could get there pretty quickly just by subtracting over. And here's, I think, where we actually need this to be an integral domain. And then factoring out. But we proved earlier in maybe the last video or the video before that we have cancellation within an integral domain. So that means we can cancel the p, keeping in mind that we can just think about this left-hand side as 1 times p. And that gives us 1 is equal to m times b. But if 1 is equal to m times b, that means that b is a unit, because we found a multiplicative inverse for b. In fact, it's equal to m. But have we done it? Well, yes, we have. Notice we've got p is equal to a times b. That implies that b is a unit. And observe, in order to be irreducible, if you've got p is equal to a times b, either a or b is a unit. Now, it could have been a being a unit if, without loss of generality up here, we had assumed that p divides b. But that wasn't the setup that we had. Okay. So next up, what I'd like to do is a follow-up result showing that inside of the integers, if something is irreducible, it's also prime. Now, of course, this is going to prove that inside of the integers, primes and irreducibles are the same. But from our previous discussion, we expected that to be the case. The really interesting places will be where primes and irreducibles are not the same. Okay, so let's see how this proof goes. So let's suppose that p in z is irreducible. And let's suppose that p divides a times b. And we'll do this by showing that if p does not divide a, then it must divide b. So I guess if you want to be like super over thorough with this, you can break this into 2 cases. So the first case would be p divides a, but in that case, we're definitely done because we have achieved the definition of a prime over here. So the second case would be p does not divide a. But if p does not divide a, that means that the GCD of p with a is equal to 1. I think that's pretty well known. But now we can use Bézout's lemma to find integers. So I'll just say there exist integers x and y such that p times x plus a times y is equal to the number 1. Now what we'll do is take that and multiply it by b. And observe that's going to give us b is equal to p times b times x plus a times b times y. But now we can use this fact up here that we started with. P divides a times b. But if p divides a times b, then that means that there exists an integer m such that a times b is equal to m times p. But that means we can replace this a times b with m times p. So here we have pbx plus mpy. We can factor a p out of this, and we'll have what? Well, it's going to be bx plus my. But now look at this equation that we've got here. We've got b is equal to p times something. But that means that p most definitely divides b. And there we have it. We have proven that inside of the integers, primes and irreducibles are the same. Up here, we show prime implies irreducible in any integral domain, and here in the integers, we prove that irreducible implies prime. Okay, so now let's look at some places where irreducibles and primes are not the same. All right, so now let's look at some examples where irreducibles are not prime. Recall, primes are always irreducibles, so this is the not that we'd like to show that they are not the same idea. If they were the same idea everywhere, then we wouldn't have 2 definitions, kind of obviously. So let's start with z adjoining the square root of -5. So this is a ring or an integral domain, I should say more precisely, that we looked at in the previous video. Now let's observe that we can factor 6 as 2 times 3. That's the standard prime factorization in the integers. We can also factor it as 1 plus the square root of -5 times 1 minus the square root of -5. You can just multiply that out and see that you kind of very quickly get the number 6. Now I'd like to make the following claim, and that is that 2, 3, and 1 plus minus square root of -5 are all irreducible, but they're not prime. Now perhaps we're not going to show all of these individually. We'll just show maybe one of them or 2 of them carefully, and then you can fill in the details for the rest of them. So let's start by proving that 2 is irreducible. And we're going to use this norm function that we used in the previous video. This is a great tool for working in these quadratic extensions of integers. So let's recall that the norm of a plus b root minus 5 is equal to a squared plus 5 times b squared. And that essentially pushes a problem happening in one of these crazy rings to something happening in the integers, which is sometimes helpful. Okay, so now let's suppose that we can factor 2. And maybe we factor it as a plus b times the root minus 5, and then c plus d times the square root of minus 5. Maybe we could think of this as alpha times beta, where alpha and beta are in this z adjoined the square root of minus 5. Now what we'd like to show is that either alpha or beta is a unit. Now what we can do is apply the norm function to this equation. So let's notice that the norm of 2 is equal to 4, just by that formula right there. But that's going to be equal to the norm of alpha times beta, but that's the norm of alpha times the norm of beta. In the previous video, we proved that this norm function was multiplicative, but then that's equal to a squared plus 5b squared times c squared plus 5d squared. Now we can use this fact, and that is that inside of the integers, 4 only factors as 2 times 2 or 4 times 1. So that means that we'll split the ways of factoring 4 up among these two factors over here. That's kind of the idea here. So we can really get off the ground and skip something with the following observation. So let's note that if b or d are non-zero, then we have a squared plus 5b squared times c squared plus 5d squared is bigger than or equal to the number 5, which is strictly bigger than 4. Now, why is that? Well, if they're non-zero, then kind of obviously we're going to have at least 1 here for the b squared, or at least 1 there for the d squared. But then that means that this number is either bigger than or equal to 5, or this number is also bigger than or equal to 5. But here we're multiplying two non-zero numbers. One of them is bigger than or equal to 5. That means that the whole thing is bigger than or equal to 5, keeping in mind that we're in the positive integers in this equation. So what does that tell us? Well, if b or d is bigger than 0, we have a problem. So that means that b and d both have to be equal to 0. But that means our equation right here immediately turns into this. So we have 4 is equal to a squared times c squared. Okay, but now let's observe that means that we have two cases. A is either plus minus 2 and c is equal to plus minus 1. Or a is equal to plus minus 1 and c is equal to plus minus 2. Here we're using the fact that the square root of 2 is not an integer, but I don't think we really need to worry about proving that. But let's observe if we have this set up right here, then beta is equal to plus minus 1, which is a unit. That's because d is equal to 0. And then in this case right here, that means that alpha is equal to plus minus 1, a unit as well. But that is what we needed to prove that this is irreducible. We factored it, and the only way to factor it is for one of these to be a unit. Okay, good. We've got this as irreducible. Now let's prove that it's not prime. All right, so now we're proving that 2 is not prime inside of this z adjoining the square root of minus 5. So let's observe that 2 divides 6, and we know 6 is equal to this product 1 plus root minus 5, 1 minus root minus 5. But pushing that together, that tells us that 2 divides this 1 plus root minus 5 times 1 minus root minus 5. Now, if 2 was prime, then 2 would either divide this term, this 1 plus root minus 5, or this companion conjugate term. So what we'll show is that it doesn't prove either. So let's maybe say that's under this note, and that is that 2 does not divide 1 plus minus the square root of minus 5. And perhaps we'll just focus on the plus version of this because the minus version of this is completely similar. Okay, so now we're going to do this by way of contradiction. So by way of contradiction, suppose that 2 divides 1 plus the square root of minus 5. But that means that we can write 1 plus the square root of minus 5 as 2 times a plus b times the square root of minus 5. Remember, our division here is happening within the integers, within the integers adjoining the square root of minus 5. But now we can multiply this out and we'll get 2 times a plus 2 times b root minus 5. But now we can essentially just extract real and imaginary parts of both sides of this equation. Observe that gives us that 2 times a is equal to 1 and 2 times b is also equal to 1. But that's obviously a problem because that means that a is equal to a half, which is not an integer, and b is also equal to a half, which is also not an integer. So remember, for this division to occur within our ring right here, we would need a and b both to be integers. Okay, so anyway, that's how you would do this part. 2 is irreducible but not prime. Now I'll leave it to you to fill in the details for the rest of these. 3 is irreducible and not prime, and then this 1 plus minus root minus 5 is also irreducible but not prime. Okay, so now let's look at some prime elements inside of this z adjoining root minus 5. Now we're going to show that 11 and the square root of minus 5 are prime in this ring that we've been working with. And I think this is pretty interesting. It means that this ring, z adjoining root minus 5, has the following picture. You've got units over here, and in the previous video we proved that the only units were plus minus 1. And then you've got irreducibles. 2 and 3 are irreducible but not prime, and there are other examples of this as well. But 11 and square root of minus 5 are prime. And remember, all primes are irreducibles. That's why I've got that containment over there. Okay, so let's see how we can show that 11 is prime. Okay, so let's suppose that 11 divides alpha times beta, where alpha and beta are our standard form in this z adjoining root minus 5. So a plus b root minus 5 and c plus d root minus 5. But observe, by taking the norm of this, we see that 121 divides the norm of a times the norm of b. But 121 is 11 squared, so that really means that 11 divides the norm of a times the norm of b. Now we know that this equation is happening within the integers, and in the integers, irreducibles are prime. So, or in fact, I guess we just really need that 11 is prime. So that tells us that 11 divides the norm of a, or 11 divides the norm of beta. Alpha and beta, I should have been saying. So without loss of generality, let's say that 11 divides the norm of alpha. And let's just put alpha equal to a plus b root minus 5 at the moment. So that means that the norm of alpha is equal to a squared plus 5 times b squared. But now what do we have? That means that a squared plus 5 times b squared is equal to 11 times m. It's a multiple of 11. Remember, divisibility can be rewritten as this multiple language as well. But now I'm going to reduce this equation modulo 11. So let's observe this means that a squared plus 5 times b squared is congruent to 0 mod 11. Now we're going to use the fact that there are only certain perfect squares mod 11. So let's make our chart. So we've got x and then x squared modulo 11. Now I'm going to use positive and negative values for x, which means I only have to go up halfway, just keeping in mind that if I square out a negative, it doesn't give me anything different than having the positive. So we'll have 0 plus minus 1 plus minus 2 plus minus 3 plus minus 4. So 1, 2, 3, 4, 5. And I guess we need one more plus minus 5. Okay, so let's observe that this is 11 numbers in the end. We have 2, 4, 6, 8, 10, 11. Now let's square these. Squaring 0 gives us 0. Squaring 1 gives us 1. 4, 9, 16, which is the number 5 inside of congruence mod 11. And then 25, which is 3 mod 11. Now, let's make a chart where we have 5 times x squared, or let's add to this chart, I should say. So let's see, that'll give us 0, that'll give us 5. 5 times 4 is 20. Notice that 20 is going to be the same thing as what? 9 mod 11. 5 times 9 is 45, which is 1 mod 11. 5 times 5 is 25, which is 3 mod 11. 5 times 3 is 15, which is 4 mod 11. Now we want to look for the ways that we can add something from this row right here, this x squared row, and then something from this row right here, this 5x squared row, to achieve 0. And that'll give us our solutions for a and b right here. So let's see. We can only add 0 to 0. We can add 1 to, well, notice there's no 10, so we can't add 1 to anything. We can't add 4 to anything to achieve 0 mod 11. We can't add 9 to anything. We can't add 5 to anything or 3 to anything. So that means our only solution here is for a squared and b squared to be congruent to 0 mod 11. But that means that a and b are congruent to 0 mod 11. But what does that mean? Well, that means that we can write a as 11 times, maybe I'll write a naught, and b as 11 times b naught. But let's observe that this line right here is exactly what we need to finish this thing off. Notice that we have alpha can now be written as 11 times a naught plus b naught square root of minus 5. In other words, we have 11 divides alpha. But starting up here at 11 divides alpha times beta and ending down here at 11 divides alpha is exactly what we need for 11 to be prime. And like I said, I'll maybe leave it to you to show that the square root of minus 5 is prime. I think that one's a bit easier. So now let's look inside of z adjoin I, so the Gaussian integers. So later we will prove that primes and irreducibles are the same inside of this set or inside of this ring. What I'd like to focus on with this example are cases inside of this ring where previous primes inside of the integers, are no longer prime. And as an example, we'll prove that 3 is prime inside of z adjoin I, but 2 and 5 are no longer prime. So let's suppose that 3 divides alpha times beta. And here alpha is equal to a plus bi. Remember here we're in z adjoin I. And beta is equal to c plus di. Now, we're going to use a fairly similar strategy to what we just used, so this might look very, very similar. So let's observe that this means that 9 divides a squared plus b squared times c squared plus d squared. There I just took the norm of both of those terms. But notice that means that 3 divides a squared plus b squared and times c squared plus d squared. If 9 divides something, then 3 divides something. But now 3 is prime, so that means that 3 divides one of those. And without loss of generality, let's assume that 3 divides a squared plus b squared. But now let's observe that means that a squared plus b squared is congruent to 0 mod 3. It is a multiple of 3. But now we can make the same sort of chart that we just made. So let's make this chart x and then x squared mod 3. And then since 3 is not very large, let's not use this plus minus trick to make it a smaller chart. Let's just use 0, 1, and 2, the kind of standard residues mod 3. So if we square 0, we get 0. If we square 1, we get 1. If we square 2, we get 4, which is 1. Notice there's no way to add two perfect squares and get 0 unless they are both 0 mod 3. Notice 0 plus 1 is 1, and 1 plus 1 is 2. Those are not 0. So that tells us that a squared and b squared are both 0 mod 3, but that means that a and b are both 0 mod 3. But that means that we can write a as 3 times a naught, and we can write b as 3 times b naught. But then putting that back up here, that means that alpha is equal to 3 times a naught plus I times b naught. Or I guess we're writing this as b naught times I. In other words, we have 3 divides alpha as needed to show that 3 is prime. Okay, so now what about proving that 2 and 5 are no longer prime? Well, we just simply find a factorization. So notice that 2 is equal to 1 plus I times 1 minus I. And then we can write 5 as 2 plus I times 2 minus I. But then what we've done is we've exhibited 2 as a factorization, including no units. Recall that our units inside of z adjoint I are simply plus minus 1 plus minus I. We factored it without units. That means that 2 is not irreducible, but not irreducible implies not prime. And then similarly for 5. And if you want to know what's going on generally here, all of the primes that are of the form 4n plus 1 are no longer prime inside of z adjoint I, but all of the primes that were originally 4n plus 3 are prime inside of z adjoint I. Okay, so now I want to look at one more example of an irreducible but not prime in a little bit more complicated of a situation before we introduce a new definition. Okay, so for one last example of a place where we've got irreducibles that are not prime, this one's a little bit more complicated. So let's consider the following subring of the rational numbers adjoin x and y. That's two variable polynomials where our coefficients are rationals. And what is this subring? Well, let's set it equal to all polynomials. So we've got a, m, n, x to the m, y to the n, where m plus n is even. So they're all polynomials that have even total degree. So that means that x times y is even because 1 plus 1 is 2, which is even. X cubed times y to the 5th is even because, let's see, 3 plus 5 is 8, which is even. Now, we can write that as the ring generated by, and we haven't used this notation before, but we could introduce this notation just to say the ring generated by these 3 elements, x squared, y squared, and x times y. Now, let's observe the following. So x squared times y squared can be written 2 different ways. It can be written as x squared times y squared, and it can also be written as xy times xy. So we factored this thing x squared times y squared 2 different ways. But what does this tell us? Well, let's observe that means that x times y divides this product x squared times y squared, but x times y does not divide x squared, and x times y does not divide y squared. I think that's pretty clear. So that means what? Well, that means that x times y is irreducible. I guess we didn't prove carefully that it's irreducible. I'll leave that to you, but not prime. So there's our other example of irreducible but not prime. Okay, so I'd like to recall that in some of the examples we've worked with factorization that is into irreducibles but not unique. We saw it right here. We factored this product xy squared or x squared y squared into x squared times y squared and xy times xy. That was a product into irreducibles in 2 ways. 2 different ways, non-unique factorization. We also saw it with, and this is coming from a previous example, 6 is equal to 2 times 3 and 1 plus root minus 5 times 1 minus root minus 5. So what we want to highlight here is in some integral domains, we have a factorization into irreducibles that is not unique. So now what I'd like to do is make a definition for a type of integral domain where the factorization is unique. And then we'll study that type of integral domain a bit. Okay, so here's our definition. We say that an integral domain D is a unique factorization domain if for all non-zero non-unit elements A, we can write A as the product of irreducibles uniquely up to associates. So that factorization into irreducibles is unique up to them being associates of each other. More precisely or more carefully, if we can write A as P1 to the R1 times P2 to the R2 all the way up to Pk to the Rk, and we can also write it as Q1 to the S1 all the way up to QL to the SL, where Pi and Qj are irreducibles, then first of all, K is equal to L. We have the same number of irreducibles, and we can shuffle the Q's around so that Ri is equal to Si. So in other words, all of those exponents are the same, and Pi and Qi are associates. So that's where I said that this is unique up to them being associates. So as a couple of examples and non-examples, I think we've seen these already, we just didn't have the word for it. Z is a unique factorization domain. That's by the fundamental theorem of arithmetic, which you're probably familiar with. Z adjoin I, the Gaussian integers, is as well, which we'll prove later. F adjoin X, polynomials where the coefficients come from a field, that in fact is a unique factorization domain. That's kind of nice. And then some non-examples, Z adjoin root minus 5 and Z adjoin 2. Here's an example of why Z adjoin 2 is not a unique factorization domain. So it turns out that in a unique factorization domain, the notion of a prime element and an irreducible element are the same. And so that's what we'd like to prove now. So now for the big result of the day. So in a UFD, so just by the way, I didn't use that over here, but a UFD is our shortening for a unique factorization domain. The notion of a prime element is the same as the notion of an irreducible element. In other words, P is prime if and only if P is irreducible. So we've got an if and only if statement here. Notice the forward direction is true in all integral domains. We already proved that. So let's focus on the reverse direction. So let's suppose that P in D, I didn't give our UFD a name, let's say it's D, is irreducible, and we have P divides A times B. So that's the setup for showing that it's prime. Now we'd like to show that P divides A or P divides B. But let's use this. Let's use the fact that we can write A times B as M times P. And let's do a factorization of A, B, and M. So we can write A as P1 all the way up to Pk. We can write B as Q1 all the way up to QL. And then we can write M as R1 all the way up to Rk plus L minus 1. We know that's the right number of irreducibles because we've got K plus L over here on the left-hand side. And then we have to also have K plus L over here on the right-hand side. P is already an irreducible, so we need one less. All right, so now let's rewrite our equation right here with this factorization into irreducibles. I'd like to point out here that I'm not using my exponents here. We can just assume that we've got repeated irreducibles here as necessary. Okay, so like I said, let's take this and rewrite it. So we've got this is equal to P1 all the way up to Pk times Q1 all the way up to QL times R1 all the way up to Rk plus L minus 1 times P. But now, since our factorization is unique up to associates like we have over here because we're within a UFD, that means that there exists either one of these or one of these that is an associate of P. Because this list over here of irreducibles is the same as this list of irreducibles up to associates. Let's assume that it's one of the PI's just without loss of generality. So there exists a PI such that PI and P are associates. Okay, cool. But associates mean they differ by a unit. So that means that we can write PI as U times P for U in D, a unit. Remember, that's what it means to be an associate. They differ by multiplication by a unit. But now what we can do is take our factorization of A and replace the PI with U times P. So what is that going to look like? Well, we've got A is now equal to P1 all the way up to PI. I'm going to put a hat over it. That means I'm removing it from the product all the way up to PK, and then times PI on the outside, but I'll write that as U times P. But notice that means that we've got A is equal to P times some stuff. In other words, P divides A. But that's where we needed to end up for this proof that P is also a prime. Okay, so now that we finished all of this, I'll leave you with some exercises. So here's some exercises for you. So the first is to show that z adjoining the square root of -7 is not a UFD. Also, go ahead and find an irreducible in this ring that is not prime, and then also a prime element. Next up, let's observe that today we didn't talk about z mod n for any n when we talked about irreducibles and primes. So there's a reason for that, and that's because in z mod n, the notion of an irreducible and a prime is not super interesting. That's not to say that there are no irreducibles. So can you find all irreducibles in z6, z8, z10, and z12? Then finally, let's determine if the following are irreducibles. So the first is 3 minus the square root of 3 in z adjoining the square root of 3. And then next is this polynomial 2x squared plus 4x plus 6 in the ring z adjoin x, in the ring q adjoin x, and then finally in the ring z11 adjoin x. And that's a good place to stop.